Conditional probability. We're going to start with a review from the last lesson, just the ins and outs of probability. So when we're looking at the probability of an event, the numerator will be the number of different ways that the outcome can occur, and the denominator is that total number of outcomes. There's three different ways that we can identify probability. One is a percentage, the next is a decimal, and the last is a fraction. So if we are identifying probability as a percentage, that's from 0 to 100%. As a decimal, that would be from 0 to 1. And as a fraction, that would also be from 0 to 1. So if we look at the three statements below, an impossible event which has 0 chance of happening is assigned the probability of 0. If an event is certain to happen, then that's 100% chance and it's assigned a probability of 1. And all of the other events will be between 0 and 1. So for the first example, it says if you roll a pair of standard dice, what is the probability that they land with a sum of 5 showing? Then we have a hint that says show your work using a chart. So I'm going to start by putting a chart in front of you so we can see what that sample space is before we identify the probability. So here is our sample space. We have the sum indicated with the numbers that are put into this grid, and then the outside are the examples of the two different die. So we could say that this is one die and this is the other die. So the sample space actually holds 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6. So that means that we have 36 different outcomes. We have 36 different outcomes. That's going to be our denominator when we identify probability. So we have probability that the sum is 5. Now, how many different ways can that sum be 5? It could be any of these combinations when rolling the die. So it looks like there are 4 different ways. Then we simplify that and we get 1 over 9. So this would be our fraction. We put that into our calculator, we get 0.11 repeating, and that's our decimal, which is the same as 11.1%. On this slide, we're just going to talk about how information can be given to us in a table. So this says that we have a table of outcomes, and we use these typically to compare two categorical variables. And when we say two categorical variables, we're saying that it's not necessarily a quantitative measure, it's a qualitative measure. So for example, a person can be male or female, and then the number is how many of each of the category we have. Or we have that car, bicycle, and bus. And then the number below is how many correlates to each category. So for example, a group of teachers were asked which type or which mode of transport they use to travel to school. Their responses are summarized in the table below. The variables are gender and mode of transport. So if we look across this first row, that's the total males. If we look across the second row, that is the total females. Then if we look down the first column, that's cars. Down the second column is bicycle, and down the third column is bus. Now we're going to be using tables to talk about conditional probability and solving for conditional probability. What conditional probability means is that we're trying to find the probability that one event happens given that we already know that a previous event has occurred. So let's look at the notation here. So for this example, we're going to say that A is the event that happens first and B is the event that is happening given that A has already happened. So look at the way the notation is. We have the B written, which is that second event. Then we have this line that means the word given. And then we have the first event. The numerator is the first and the second event occurring. So this little symbol here that looks like an upside down U is the word and, the word intersection. And the denominator, instead of the denominator holding the probability of the entire, it holds the probability of only event A, so only the first event. And the reason why we changed that from being the entire sample size to just the sample size of A is because we already know that event A has happened. So this is the first event. You will need to know this formula. Look at it, study it. Now, not all of these examples have conditional probability, so you'll see a mix of examples here. People exiting a new ride at a theme park were asked whether they liked or disliked the ride. The results are shown in the table. Use the table to estimate the probability that a randomly selected person who went on the ride, A, liked the ride. Now, before we actually answer, it's important and it makes our life easier if we actually total these rows and columns. I'm going to put a total here. Now, if you add 55 plus 17, we get 72. If you add 28 plus 30, we get 58. So that's adding our columns. If we add our rows, 55 plus 28 is 83, and 17 plus 30 is 47. Then if you add 72 plus 58, you get 130, and if you add 83 and 47, you will also get 130. So we have our totals. Now let's go back to the question. For A, the probability that we liked the ride. So we're just asking how many people liked the ride out of the total number. Well, the total number is 130, so that's going to be in our denominator. And how many liked the ride? We're going to look at the top row, and we're going to look at the total, which is 83. Then we always want to look and see if we can simplify it. We can't simplify it, so that's our final answer. Now we're going to go to the next question. What is the probability that the person is a child and disliked the ride? So the probability of child and disliked the ride. Now we're not given two different events that we're saying that one event happened given that another event has already happened. And because we don't have that designation, our denominator is still 130. Our numerator is going to be that intersection of child and disliked. So if we look at our table, we look down the child column and we looked for disliked, and our answer is 17. So the numerator is going to be 17. We simplify, we can't simplify, so we leave it as 17 over 130. For C, it's asking the probability that we have an adult or disliked the ride. So again, we're not looking at our conditional probability yet because we're not told that one event has happened given another one has already happened. So let's write down what we're looking for: adult or disliked. disliked. So our denominator is still going to be 130, the total. And our numerator, let's look at our columns. We have adult, and then we also have disliked. The fact that we see an or means that we're adding our numbers together. Well, here's the problem. That 30 is actually being counted twice. If you look at how the highlighting went, it was counted once for being an adult and once for the disliked. So that means that that 30 is double counted. So we have to make sure that we subtract the 30. So we can look at the total for adults, that's 58. We look at the total for disliked rides, that's 47. And then because the 30 is counted twice, we subtract 30. So we end up getting 75 over 130. You may notice that that numerator is our same formula for mutually exclusive events when we have an intersection of the events that we talked about in the last video. You can also get the sum of 75 from adding 17 plus 30 plus 28. Now let's look at D. What's the probability that we liked the ride given that he or she is a child? So now we have this given. So you can think of it as event A is the fact that we know that this person is a child. That is our given. So event B will be the fact that they liked the ride. So the probability they liked the ride given that the person is a child. So how do we set that up? Our numerator is the intersection between liking the ride and a child, and the denominator is the given, the fact that the person is a child. So instead of having that 130 as our total in our denominator, we don't need to account for the adults as a possibility because we already know that it's a child. So our denominator is going to be 72 because that's our probability of being a child. Then the numerator is going to be that intersection between they like the ride and they're a child. So they like the ride and they're a child is 55. So our answer is 55 over 72. E. Find the probability that we have an adult given that they disliked the ride. So what we know to be true is that the person disliked the ride. So that's going to be that first event. The fact that they are an adult is their second. So probability of being an adult given they disliked the ride. So our numerator is the intersection between the two events. And our denominator is what we already know to be true. We already know that this person disliked the ride, so we don't need to account for the total that they could possibly like the ride. So they disliked the ride, that's 47, and being an adult and disliking is 30. So our numerator is 30 and our denominator is 47. Were the probabilities in example 1 experimental or theoretical? What is the difference between experimental and theoretical? So we will do the definitions first. Experimental probability means that the data was collected from actually doing some sort of experiment. Versus theoretical probability means that the data is based on what you expect to happen. So you're not actually doing an experiment. So here's an example. We have a coin and we are going to flip the coin. If we're doing an experiment, we say that we're going to flip the coin 50 times and we're going to record how many times it lands on a head. Then we actually do the experiment and calculate the probability of flipping a head when we flip a coin. Versus theoretical is we identify that the probability of flipping the coin and having it land on a head is 50% because there is only one way out of two to achieve a head. So let's go back to our question. Were the probabilities in example 1 experimental or theoretical? In example 1, they were experimental because there was actually an experiment conducted where they asked people if they liked the ride or not. Example 3. Skyline has taken a survey of statistics students and found the following about their eye color. So here is our table of outcomes. You'll notice some gaps in our table of outcomes, so we need to fill in some information before we can get started. And then we have our 3 questions below. So our categories are gender and then color of eye. If we look at our columns, we can total our columns. So if the total is 1 and we have 1 male, then that means that this has to be a 0. For the blue, we can take 8 and add 5, so we get 13. For brown, if the total is 20 and we already have 8, that means we need 12 more. For green, we will add the 4 and the 1 to get the 5. And for hazel, we know that the total is 2, but we already have 0, so that means that we need 2 to fill in. And then our grand total is going to be 41. What is the probability that a randomly selected student would have green eyes? So there's no condition on this, so it's out of that total of 41. So the probability of green is going to be out of 41. And if we look at the total of green, that's going to be 5. So that will be our numerator. For B, what is the probability of a randomly selected person being a female? I'm going to do B down here. So the probability of female, again, we don't have that conditional, so we have the denominator, which will be a total of 41, and then the female is going to be 22. For C, given the student is a male, what is the probability that he has brown eyes? So the given statement is here, so that's going to change our denominator. So the probability, now what we know goes after our given line, and we know that the person is male, and then brown eyes. So our numerator is going to be that intersection between brown and male, and the denominator is going to be the fact that we already know that the person is male. So our male total is 19, and the intersection between brown and male is 12.